In our project, we try to analyze a legged hexapod, which can be simply tough like a spider with 6 or more legs. Now, the study of that kind of robots is still in development and complex due to the great number of problems which raise in the control of their working strategies. In particular, a legged hexapod should be able to adapt his work with respect to the ground characteristics. So there exist several ways to move his legs, hence different typologies of periodic gates, and it is possible to modulate the force that legs apply on the ground. Essentially, legs can be alternately in two configurations, the rest phase and the swing phase, which allows the robot walking. Our study started choosing a 6 legs types and modeled each leg as a 3-leg arm, having 18 degrees of freedoms in total. Firstly, we have applied the identity Hunterberg convention and we have found the parameters alpha, theta, d and l, where L1, L2 and L3 are the length of the 3 links composing each leg. Also, we have imposed the joint frames as it is shown in figure, and then we were able to calculate the homogeneous matrix and both the direct and inverse kinematics of one leg. Then we have calculated the Jacobian matrix, from which we have realized that the hexapod singularities are the femur one, the tibial one, and the case of two legs collision.
The study of the statics of the robot legs was performed in order to obtain the values of the torques to correctly apply in the joints, and to verify that the chosen electrical motors can provide such torques. It is assumed that the only external force acting on the end effector is gravity force, and that the mass is equally distributed in the body, so that it can be performed a one-leg study. The dynamics have been calculated in the Newton-Euler formulation on a predefined trajectory, but for the control part it has been used a different decentralized approach, which will be discussed next. Following steps are in fact the analysis of trajectories and control strategies.
To implement the trajectory planning algorithm, Simulink, and in particular StateFlow, have been employed. Given the expected pose of the hexapod, its inverse kinematics can be used to determine the associated joint angles, which in turn can be used to compute the polynomial trajectories in the joint space. In order to do this, a default configuration for the legs has to be defined, so that each step, 3 of them are raised and moved to such a configuration, while the others keep their ends in place, ready to be lifted in the following steps. The real pose and joint angles are sampled, so that the real positions of the legs required to stay in place can be determined and used in the computation of the expected trajectory in the joint space. By taking into account the real pose of the hexapod, the unavoidable errors in the task space trajectory can be kept within acceptable bounds.
To control the system, we have chosen a decentralized control system based on two levels. The high level is the generator of the trajectory before described. It does the adjustment of the hexapod trajectory and orientation, measuring the real coordinates of the barycenter and RPY angle of the central body. It gives in output the expected joint angle. Instead, the low level controls each joint individually with a PI controller. First action is to take as input the joint position from high-level control and transform it in joint torque. The result is put in the escape simulation that returns the real position in feedback. A simplified model of the hexapod with characteristics similar to those of the Phantom X has been implemented and simulated with SimScape multibody. The masses of the motors have been neglected, while the viscous friction at the joint are keeping in consideration, in order to avoid unrealistic behavior such as the one shown.
As it can be observed, the modeled hexapod is able to move quite smoothly. Even though it exhibits some vibrations, they do not disrupt its motion significantly. The hexapod is able to follow the expected trajectory in a satisfactory manner, whether it is straight or curvilinear, and the range of the pose error is quite limited if compared to the scale of the hexapod movement. It can be observed how the torques exerted allow the joints to follow closely the planned trajectories without saturating to its maximum values. It is interesting also how the joints follow much better their desired trajectories when they are raised, When instead the leg is required to keep its hand in place, the angle of the first joint presents both an undershoot and an overshoot, while the other two struggle to compensate the errors that appear. This is due to the gravitational force, as well as the effects of the coupling between the links of the legs and between the legs and the central body.
In this last section, we want to simulate the Hexapod robot with a ROS implementation. Our work is based on a model inspired to the Phantom X Hexapod, whose description and working strategy is defined in the package Phantom X description and in the walker.py script. At this point, we implemented the 18 controllers using a PID controller. In our case, they need to be tuned in order to have the desired behavior. Now we have all the elements to launch the gazebo simulation. However, at this level, to move the Hexapod, the presence of the user is still necessary. So the next step is to make the robot capable of moving to a preset position. To achieve this task, it is necessary to implement a node that publishes and updates the position when the robot is moving towards the goal point. With this node, it is possible to know the position of the robot with respect to the environmental frame, making the information available by the script test.py. At this point, the message is read by a subscriber that exploits the odometry to move the robot from the initial position to the goal point, setting and updating the robot velocity. Now we are ready to go, and at every step the updated position is shown. According to the implemented script, the maximum velocity is set to maintain the stability, and when the robot is very close to the goal, it will slow down until it will stop. With this last implementation, we are satisfied of our work, because we have analyzed the Hexapod robot in many interesting ways and enriched our preparation in robotics. Thank you for your attention.